welcome to video 3. In this video we will work on writing formulas and naming ionic compounds that contain multivalent cations, and we'll also talk about hydrates. First, keep in mind that many of the elements in the periodic table are not monovalent, and they do carry many charges, but that doesn't mean we can't name them. Basically what it amounts to is that we can use the information in the chemical formula to tell us the charge on that multivalent cation, given the fact that we would know the charge on the anion. And if it's given as a written compound, we use a certain style of naming where we include the charge of that multivalent cation in parentheses after we name it. So this example, manganese has 7 oxidation states. Now that's crazy. It's there's zero predictability to that if you don't have more information about the situation that the manganese is in. So what we need to think about here is, how do we name it then? So here below is a copper 1 chloride and copper 2 chloride, copper 2 sulfate. 2 different types of copper bound to 2 different things, but it doesn't stop us from naming it appropriately. If we know chloride's charge is 1-, and we say this is copper 1, that means copper is 1+. Okay? We have to give a stock number charge on a multivalent cation, or you can't name it properly. Now, some of you may not know Roman numerals, so I'm going to give you a brief lesson. 1I means 1, 2I means 2, 3I means 3. IV means 1 less than 5. Follow that. 1 less than 5 is 4. V is 5. An I following V means 1 more than 5, which is 6. 2 after is 7. 3 after is 8. So the V means 5. The 1 means 1. So the rules for writing formulas with ionic compounds containing multivalent cations is write each ion. Remember, the cation charge is in parentheses given to you. Then we're just going to balance charges like we always do. Lead 2 means Pb2+. Oxide 2-. And then we're going to satisfy charges. Well, these are going to live in a 1-to-1 ratio, PbO. Tin 4 sulfide. Tin 4 sulfide. Sulfide's in group 16 like oxygen, so it's 2-. So when we think of this, we're going to have 2 sulfide to satisfy tin, so it'll be SnS2. You could initially say, well, I need, you might say that's 4-to-2 ratio, but either way you would reduce to get a SnS2 charge, or SnS2 formula. So let's do a couple of examples. The first one's done for us here, iron 3 iodide. Here's iron 3, and then iodide we know from group 17. We would need 3 iodides to satisfy iron, FeI3. Lead 2 nitrate, Pb2+. Nitrate. Notice we're throwing in a polyatomic ion. We still need to know what we learned in the prior lesson. Nitrate can only take 1. Lead has 2 to give, so I need to have 2 nitrates to go with my lead. Manganese 7 oxide. Wow. Manganese 7+. Oxygen group 16, 2-. So we need to find lowest common factor of these two guys. It's going to be 14. So I'm going to have 2 manganese, 7 oxygen. Wow. How do we name ionic compounds containing multivalent cations when we're given the formula? This is a little different. So first we need to write each ion. We have to determine the charge on our multivalent cation. The good news is since we know this compound, COCl2, must have an overall net charge of 0, we can work backwards to find out cobalt's charge. If we know that 1 chloride has a -1 charge, and there's 2 of them, then overall there's a -2 charge coming from my anions. That means my cations must be correcting for it with a +2. So it's cobalt 2 chloride. That is the information I got there. Chloride is chloride, we know it well. metal, non-metal. Keep in mind you're still beginning by looking at what do I have in my compound? A metal and then a non-metal. Okay, that's ionic. Well, cobalt's got multivalent charges, so I've got to find out its charges. I don't know it by looking. Chlorine's -1. There are 2 of them. For a -2 charge, cobalt must be +2. So let's do a few together. And we have tin and then carbonate. Okay, tin and then carbonate. Again, ionic naming, we don't have to worry about how many of things there are. So really, we just name them by what the ion's name is. So tin and carbonate are dead. But the thing is, since tin's multivalent, we've got to write a charge in the middle in Roman numerals. So carbonate's always -2. And there's only one of them here. Don't think that means there are 3 carbonates there. There are not 3 carbonates. There's 1 carbonate. That means if that's -2, then tin must be +2, so it's tin to carbonate. Here I have tin and I have fluoride. Because tin is multivalent, I've got to put something in parentheses here. I've got 4 fluorides, each -1. Overall -4 charge means tin must be 4. IV is 4. Tin and nitrate, not tin, titanium and nitrate. Titanium and nitrate. Whew. Nitrate's always -1. There are 4, so that means that we have an overall -4 charge again. So that means titanium is also titanium, 4 nitrate. Iron and phosphate. All right, phosphate. There are 1 of them. Okay, I have iron, phosphate. So phosphate carries a common charge of -3. Oops, -3. So that means iron must be +3. So it's iron 3 phosphate. The next thing I want to talk about is naming hydrates. Now, we've spent time talking about ionic compounds and naming ionic compounds. Well, that's awesome. Most ionic compounds, though, when I go get them out of the stockroom for a lab, they don't come just as this in the bottle. And the reason for that is, though this is a stable ionic compound, it still has some charges that are latent in the substance when this forms a salt. What happens is it's attractive to water that's in the air. Because it's attracted to water, we have molecules of water bound into the crystal. So instead of being brown, like anhydrous copper 2 chloride, which means there's no water molecules in it, it ends up being blue, like this. This is hydrated copper 2 chloride. Water molecules have bound into the crystal. Instead of having this dry powder, I've got a larger moistened crystal specimen here, basically. The water is not part of the chemical substance, and this is reflected in the way we name it. Okay? Alright, so we name this copper 2 chloride dihydrate. This is copper 2 chloride anhydrous. Now, we won't use anhydrous a whole lot, so often when we write copper 2 chloride, it'll be just like this. Okay? The thing is, this is not just copper 2 chloride that does this. Most ionic compounds attract water from the atmosphere, so most ionic compounds in my stockroom are hydrates. So when the water is put into the crystal, we have 2 different looks. The cool thing is, though, when you put a small sample of this into water and put a small sample of this in the water, when they dissolve in water, they look identical now. Okay? Just that they're going to have a different mass because you have hydrates that have a larger mass than the anhydrous counterparts. So here's an example. Cobalt oxalate dihydrate. The di comes from 2. The prefix di means 2. Looking at the crystal, what we see is there's some repeating units. Okay, and I've boxed out what we're looking at. This is a cobalt ion that's got a +2 charge. It's bound to 2 water molecules and 2 oxalate molecules. This is oxalate right here. Okay? This is my cobalt with a +2 charge. Here is another oxalate molecule. So I've got an ionic compound with this repeating unit of crystals tagging to each other, but there's room in each cobalt molecule for 2 waters. Okay? So the anhydrous, these waters wouldn't be here. But if it's exposed to atmospheric air, these water molecules bind on, and you get cobalt oxalate dihydrate. Cobalt, 2 oxalate, dihydrate. Cobalt is a Cobalt is a multivalent cation, oxalate is a polyatomic ion, and that's hydrated. When you see this little dot between them, it doesn't mean multiply. It just means that this is attached to this. It's not part of the chemical formula. It's not changing how cobalt 2 oxalate behaves very much. It's part of that crystalline structure. So, pretty simple stuff. We're going to use ionic naming rules just like before. We'll follow the chemical formula by adding a dot and then a hydrate preceded by the prefix and the number from the number table below. And this is something we'll memorize over the course of this unit. And I'm going to urge you to write this down and keep it handy throughout our practices because we use it more than once. Of course, you're going to memorize it by the time we take the test, but by the time you get there, I think it should be no problem. So let's do sodium nitrate trihydrate. Sodium ion, this is a metal, this is a polyatomic ion bound to it. Pardon me. Sodium nitrate. So I just need to bind these two together, and that's sodium nitrate, 1-to-1 ratio, dot trihydrate. Tri means 3 waters. Sometimes you'll hear this referred to sodium nitrate 3 waters. Example or two, calcium carbonate dihydrate. Calcium is 2 plus, carbonate 2 minus. Okay, so that's a 1-to-1 ratio. Calcium carbonate dot 2 waters. Zinc sulfate monohydrate. Zinc is one of our monovalents. That's kind of weird. It's 2 plus. And then sulfate, SO4, 2 minus. So again, 1-to-1 ratio. Zinc sulfate monohydrate. I don't need to write the 1 for mono. Aluminum perchlorate nonahydrate. Wow. Aluminum, 3 plus. Perchlorate, 1 minus. So I gotta have 3 perchlorates per aluminum. So there's my aluminum, perchlorate, 3 of them. The dot and a nona. Nona means 9. I almost wrote N. 9 waters. Let's look at it the other way. Normal ionic naming rules, meaning name each ion, then name the hydrate parts. That's so simple, right? So we have our example, MgSO4 7H2O. We have a metal, non-metal, got it, metal and a polyatomic ion, sulfate, and then 7 waters. So I'm going to write magnesium. My handwriting's going to get sloppy here because I tend to get sloppy. And there's no dot here at all. You just write magnesium sulfate. Duh. If you've forgotten them, they're at the bottom. Hydrate. That's one word. Sandwich that back together right there. That's one word. So let's do a couple. We had 10. Oh no, we got polyatomic. Sorry, not polyatomic. We got multivalent cation. We got chloride and waters. Fun. Chlorine, we know group 17, that's always -1. So we have a -4 overall charge, means 10 must be +4. So 10, 4, chloride, pentahydrate, 5 waters. We have gallium and fluoride here, -1. Gallium typically is +3, but in this example, we're letting it be polyatomic. Or no, sorry, in this example, strike that. Gallium is always +3. Forget I said anything. Gallium's got a +3 charge. So we need 3 fluorides to react with gallium there. Gallium, fluoride. No parentheses needed. Monovalent cation. 3 waters. Trihydrate. Finally, we have the acetate ion. That's a polyatomic with a 1- charge. We have nickel. Oh, nickel's a multivalent cation. I got on a roll with the multivalents on gallium. I apologize. So if we have 2 acetates, that's an overall -2 charge. So nickel must be +2. So it's nickel 2 acetate. Notice I didn't change the name at all. Left it exactly as it is. Tetrahydrate. Exceptional handwriting for me. You can read it. that concludes our video for naming ionic compounds containing multivalent cations and hydrates. If you have any questions, please see us in class. I expect you to take in high-quality notes. Notes for nomenclature are quick and easy. We really need to get you in practicing in class, so make sure you come in with a good handle on this so we can move on to the next nomenclature topic. We'll see you in class.